Again, welcome everyone. Thanks for joining. This is the third of 3 webinars that MTS is hosting at different times, different geographies to accommodate people around the world. Today, we're going to be talking about structural test solutions in the eVTOL market. A couple of bits of housekeeping before we get started. Just based on the number of people that registered, we've muted the mics. We will plan to address questions at the end of the session, but you can post questions using the chat function in Teams along the way, but we're going to address the questions at the end, and we are recording the session. Let's get started. Here's a quick outline as to what we're going to cover today. We'll do some introductions, a brief overview on MTS, and then we'll really get into our expertise and background when it comes to testing, aerospace testing, with a specific focus on this market. We'll talk specifically about test types, including materials, components, then moving to full-scale tests, including system integration labs, iron birds, and then full-scale static and fatigue test setups. And then hopefully we have some time at the end for questions. The plan is to run 40 to 45 minutes or so of content and then have time left over at the end for questions. Okay, introductions. This is me. My name is Jeff VanLangendon. I've worked at MTS here for 17 years. I'm based out of MTS headquarters here in Eden Prairie, Minnesota. I've been supporting the aerospace structural test market pretty much since I started here. I've primarily worked as an application engineer, and since then I've added a couple different roles. Most recently, I've added some business development responsibilities, but I still continue to work with customers with a primary focus on full-scale testing in the aerospace market. My wingman today, although I'm not sure he's on because it's an unusually early hour in Europe, this is Jonas Björ. He and I tag team to put together the presentation. He hosted the session in Europe. Jonas has, I guess, twice as much experience as I do. He started as a customer using MTS equipment, testing airplanes at Saab in Sweden, and he's had multiple roles at MTS, including systems integration engineer, application engineer, product management, and today he's filling the role of application engineering manager, and he again works out of the Berlin office. Okay, again, the focus today is the electrical vertical takeoff and landing vehicle market. We'll talk about what MTS sees as similarities and differences when compared to more traditional fixed wing and rotary wing aircraft. We'll talk about the challenges that we've observed in this market in terms of how these vehicle and platforms are tested, and then how we've helped customers in this space. What's interesting to us about this classification of vehicle is that it comes in many different form factors. So eVTOL is this broad category of vehicle. And there's lots of differences when it comes to the mission profile, the range, the capacity, number of passengers, whether or not the platform is piloted or unpiloted, and just the overall design approach as to how these vehicles fly. We'll discuss test technologies and methodologies that are transferable, again, from the markets that we've been working with for a long time, including fixed wing, helicopter, and then some influence from our ground vehicles market. Again, we'll discuss what we've learned after working with customers, with several eVTOL customers over the last 5 to 10 years as the market has matured. Okay, just a real brief overview as MTS, if anybody's not familiar with MTS. We're a global supplier of test and simulation systems. We are headquartered in Eden Prairie, Minnesota, where I am now. As of 2021, we became part of Illinois Toolworks. We maintain 1,700 employees. We're based as an engineering company, and we have over 250 patents since we started in business, which we started in 1966. And so we're approaching our 60th year in business. In terms of where we fit, the aerospace market fits in terms of inside of MTS. So MTS serves multiple industries. As you can see here, materials, aerospace, automotive, civil, biomedical, rail, energy, and rock. We're loosely organized, or I guess we're not loosely, but organized into 3 different business units: structures, materials, and ground vehicles. And aerospace and civil engineering make up the structures segment of MTS's business. Okay, a little bit of our background in aerospace testing. So we've been helping companies test things that fly for, again, almost 60 years. And so this includes fixed wing, helicopter, launch vehicles, satellites, and then drones, both large and small. And so just some background into some of the things that we've worked on. So what you see here is a scaled down version of a launch platform. It's a composite tank. What you see here is a helicopter test rig. So it's a blade test system. I think this is in Europe. And here's a more classic fixed wing. This is the tail section of a Cessna full-scale component. So what we see with the eVTOL market and its test requirements, what we're starting to kind of realize is that this market represents a hybrid of several legacy vehicle technology types. And so it seems to be a combination in terms of the test requirements for what we have seen historically in the fixed wing market, the helicopter market, and then there's a certain influence that we have experience with in electric vehicles, and so the battery portion specifically. And so you have this hybrid of different technologies that we have familiarity with, and now we're just putting them all together. Some other kind of show and tell of some of the big platforms that we've worked on. This is the Hawk lead-in fighter full-scale fatigue test. This is the Dassault Falcon. So this is in France. This is the Griffin fighter. Jonas had to make sure that we had a picture of the Griffin fighter from Saab in Sweden. This is the Eclipse airframe. This was tested at Southwest Research in Texas. What was something unique about this particular airframe, metallic airframe and wing, but instead of the classic rivet style assembly, this particular airframe was assembled using friction stir welding. So different assembly technology, which was pretty cutting edge at the time. This is from the original 777. So I think this was tested in the 1990s up in Everett in the Northwest. Coincidentally, the new 777, the 777X, is currently being fatigue tested, also in Everett. What you'll notice is a lot of these pictures are dated. What we found over the years is that customers are less and less willing to provide pictures of their tests and test articles. So a lot of these pictures are a bit dated. This is the Airbus A350, again tested in France. This is the Bombardier. This one's a little more recent. This is the Bombardier C Series, or what was known as the Bombardier C Series full-scale static test, which is now known as the Airbus A220. This particular static test incorporated 200 loading actuators and 8,000 strain gauges. And this is the Boeing 787 full-scale static test. I think last but not least, on the military side, this is the Airbus A400M. Okay, so is the way that we think about testing at MTS, we think about a test pyramid. And so we do have test solutions for all levels of the test pyramid. As you start at the bottom of the pyramid, we're talking about materials and coupon level testing. And as you graduate up the pyramid, what you have is the number of test articles decreases, but the complexity and the relative value of the test article increases. And so as you move from coupons up to elements, components, all the way up to the top of the full-scale structure, if you break a coupon in a load frame, typically you're just going to grab another one out of the box and start testing it. If you break a full-scale test article when you didn't mean to, it's going to cost lots of time and lots of money to get the schedule back on track. The focus today is going to be on the components and full-scale structure side. We'll touch briefly on the materials side, but the focus today is really going to be on components through full-scale structures testing. Okay, one slide on materials testing, because it is a big part of MTS's portfolio. We have an entire business unit dedicated to materials test solutions. What you see here is a cross-section of the product offerings that we have that serves that market. So static and dynamic load frames, extensometers, different types of grips, fixtures, chambers for different environments, hot, cold, wet, dry, and then all kinds of different load cells and force transducers. So in this space, our customers are looking to characterize either existing materials in a new application environment or spectrum, or potentially characterizing new materials to get material allowables. So we've seen a lot of work over the last 10, 15 years on the composite side as customers are looking to characterize the performance of different materials in an existing application. Okay, again, the focus today is going to be on different test types when we start looking at components all the way up through full-scale fatigue and durability. So this is where we're going today. Component testing, we'll talk about flight control systems tests, systems integration labs, some people call them iron birds, and then we'll talk about full-scale static testing. A subset of that is air loads calibration testing, and then finally full-scale fatigue and durability testing. Okay, starting with component testing, one of the things we're seeing in this market is the need to test batteries. And so the challenges that our customers have faced is trying to get accurate replication of time histories, again, applied in multiple degrees of freedom. This is typically a higher frequency environment. And so we've developed test systems for this market, again, largely based on our experience in testing batteries for electric cars and vehicles in our ground vehicle space. And so we have a motion platform that you can kind of see inside the circle there under the batteries. And this type of test lab can incorporate not only the motion platform, but an environmental chamber to replicate the conditions in service. Typically, there's a battery management system, and so we're putting power, we're cycling, charging, and discharging the batteries while in the flight condition. There's a lot of specimen monitoring for the safety of the test in the article. There's typically an evacuation system. So in the case of a thermal runaway, a lot of times we've assembled systems for testing batteries where the entire system is on rails that can be quickly moved to a safe location in the case of a thermal runaway. And then the other consideration we work with customers on is based on the size and scope of not only the test article, but the lab, whether or not a seismic mass is required. So again, staying with the kind of component test, and I guess leveraging what we just talked about in terms of the motion platform, depending on the size of the platform, and we make these platforms, these 6-degree of freedom platforms in different sizes and capacities and performance levels, based on the size of the platform and the size of the test article, whether it's full scale or scaled down, we have had customers who have put the entire test article on the platform. And so again, we're really leveraging tools that we've developed in our ground vehicles market. What you're seeing here is the MAST table, multi-axis simulation table, in order to apply high-frequency content and time history, which will allow our customers to characterize the performance in flight-like conditions and really assess how the structure responds. And so typically, the structure is going to be instrumented to determine what the impact of different flight conditions has on the life of the structure. Okay, another big section of component tests that we've been helping customers with is some combination of the propeller or blade system, which many of these vehicle platforms deploy. And so the challenges with this type of test is that you typically have multi-axis loading, whether it's a propeller, full-scale blade, or a blade section. You have multiple multiple axes that you're loading at the same time. Typically, there's going to be some high frequency content if you're talking about blade flap-wise or chord-wise bending. And then a lot of times on the blade, you're going to want to apply a high CF force. And so we've deployed different combinations, as you see here, of single-ended and equal area double-ended actuators. The other challenge that our customers face with this type of test is friction. And so what you want is high performance actuators with low friction, especially on the high frequency content that you're putting into the test. The other thing that we've helped customers with is control compensation and then phasing of several actuators. And so we've developed lots of tools on the hardware and software side, again, really to support the helicopter market in terms of phase and phase control. If you have multiple blades on a hub, and so the phasing of the loading, we can control for all of that, the compensation to apply the loads accurately, so that in the end, what you end up is representative loads and strains on your blade sections. Leveraging, again, our expertise from the helicopter test market, what we've commonly seen is customers are commonly targeting a specific strain field in a certain section of the blade. And so the customers spend a lot of time trying to get the exact right loads in multiple axes to achieve the target strain level. And then once they find the right combination of loads on multiple actuators to get the strain that they want, they then cycle and put hundreds of thousands or millions of cycles on the blade in a fatigue test type setup. Okay, so we're going to graduate from component testing here to one version of a full-scale lab. What we're finding in this market is that many customers are targeting this systems integration lab, sometimes referred to as an iron bird, depending on how the test is laid out, before they approach full-scale static and fatigue. So different customers use different versions of this lab, but in short, what this lab is doing is allowing the customers to put together a flight-like aircraft to allow them to test aircraft hydraulics, controls, software, and any movable surfaces, any movable mechanisms on the aircraft, which can include flight control surfaces, tilt rotor if you're moving your propeller or lift cruise propellers in different axes, can also include things like landing gear and landing gear doors. So customers build this systems integration lab so that they can ring out all the different subsystems of the aircraft using as close to high fidelity or really high fidelity versions of the power systems on the aircraft, so electric and hydraulic. One level up from a systems integration lab is the ability to put loads, external loads, on any of these moving mechanisms. So flight control surfaces, landing gear doors, and any kind of lift cruise, tilt rotor, if that's the mechanism that is used on that platform. So then the ability for a pilot in a simulator to move all the surfaces, and then again, the next level up from there is for MTS to come in and put loading actuators on all of those surfaces so that they get representative feel and work done on the aircraft as it would be seeing air loads in service. So the challenges from our standpoint, or from our customer standpoint, for this type of really complex integrated test, from a loading standpoint, is we're trying to apply prescribed or real-time load commands to moving surfaces. So that's the big difference here between materials testing or even full-scale static and fatigue. Instead of us just pushing loads against a spring, so to speak, we are now trying to follow a moving surface and apply load at the same time with high accuracy. And again, the target for our customers, with the goal here, is always to provide and apply representative loading for what the aircraft and mechanisms and subsystems will see in service. So another representation, I guess a little more schematic here, of this simulation systems integration lab or Iron Bird lab. You can kind of see how the system is laid out. One of the big challenges here, the biggest challenge, at least in my opinion, for this type of test, is you have a surface that's being moved by the aircraft control system, and you have a load actuator that's being controlled by the MTS load control system. So two different actuators being controlled by two different control systems, but they're mechanically coupled at the surface, either a real surface or a simulated surface. So what ends up happening is when the aircraft surface is commanded to move, you end up with an artificial load spike until the loading actuator recognizes the error and corrects for it. And so we've developed specific tools, both hydraulics and control-wise, to reduce and virtually eliminate that initial error spike that you get when you have the surface moving on the aircraft side. The types of tests that we see customers in terms of graduating level of complexity when we're loading surfaces or landing gear or tilt rotors. One simple test that we do is a static test. And so we'll have the aircraft control system hold the surface at position, and they will need to certify that it cannot be backdriven to a certain load. So we will ramp up the external load on those surfaces to ensure that the flight control system, which includes the hydraulics, the structure, and the software, cannot be backdriven to a certain level. So that's kind of the first basic test. They hold position, the aircraft holds position, and MTS ramps up load. The next level of complexity is kind of what you see in the lower right-hand corner. And so if a customer is going to sweep the surface through a normal kind of flight operation, we can put lookup tables into the software. If the customer knows and has a prescribed relationship between angle or position and load, we can put that information into the control system through our software application, so that as the surface sweeps, our load control system knows exactly which load needs to be applied at any given position or angle. And so we see customers use this. You can have different tables based on different airspeeds. And so you can imagine that higher airspeed is going to lead to higher loads on all the surfaces. And so you can load multiple tables and have this prescribed relationship between position or angle and load on every single channel. The ultimate in complexity for this type of Iron Bird test that we've seen is if you have a real-time dynamic command. And so if you have a pilot moving the surfaces or running through a flight simulation, the customers will typically have a flight sim computer that takes all the input from the pilot, all the subsystem data from the aircraft, and then is calculating real-time what the external loads need to be so that it's representative like it's in flight. So in that case, we've again developed tools and interfaces for us to be able to interface with that real-time flight sim so that we can be applying dynamic and randomized loads, again, based on the subsystem from the aircraft. So that's kind of the ultimate in simulation, is us taking real-time commands from a flight sim based on hundreds of different parameters that will generate a single load for us on each channel. This is what one version of an Iron Bird looks like in practice. This happens to be the Gulfstream G650 Iron Bird. This is what you see is it's a multi-channel test. So in this case, it was 12 surfaces. So from our standpoint, 12 loading channels. But really the way this works is because there's no mechanical coupling between the surfaces, the way this functions is 12 one-channel tests that are all happening at the same time. And so you can kind of see why some people call this an Iron Bird. The reason that some customers lay the system out like this, why does it have to look like an airplane? It doesn't have to, but the reason some customers do that is they want a spatial representation of the aircraft. And the reason they want that is so that they can have the correct hydraulic runs and electric cable runs on the aircraft side. They want everything on the aircraft side to be as representative and high fidelity as possible. And so they want a hydraulic power unit to each flight control actuator run to be exactly the same as it is on an actual aircraft. And so they'll lay the system out, but again, they're mounting these surfaces and actuators on a steel frame. Again, there's no mechanical coupling from our standpoint between the surfaces. Okay, we're going to move on to full-scale static testing. Again, this is one of my favorite pictures, a representation of a full-scale static test. This happens to be the Boeing 787. It was composite, obviously composite fuselage, composite wing. And so what you see here is this really dramatic view of what happens when you apply 150% of the limit load, so 50% higher than any load it will ever see in service, is part of the certification and on the critical path to the first test flight of the aircraft. I think this particular test, the deflection of the wings was something like 35 feet from its zero-G condition. So this really dramatic wing upbend, which again is on the critical path to opening up the flight envelope and allowing the flight test to start. So what does a static test look like in terms of load control and profile? And what do our customers use this for? So in general, what they're doing is they're using the full-scale static test to prove the static strength of the airframe. They use it to verify computer models, finite element models that were generated during the design. They need to determine that there's no permanent deflections that remain after they get to that limit load, and especially no failures before they get to that limit load. They're going to be constantly measuring deflections and strain on the way up. And again, the last thing that they might do is determine structural strength in case they want to consider certifying for higher loads in the future. In general, these are slow, methodical tests, right? Static tests, the tuning is not super hot. You want conservative P gains when you're testing this. These tests may take months or years to assemble, but each test case is typically only a matter of minutes or hours. So they'll run multiple test cases. And as you can see here, it's a slow and steady graduated increase in typically 5 or 10% increments as you work your way up to the ultimate load. The challenges that our customers have with running this type of test is first, you're trying to coordinate the loading between, upwards of either tens to hundreds of actuators. So again, with the goal being, you want representative loading. You want all your actuators to be coordinated and synchronized so that they all reach their target end level, whether it's 10% or 150%. You want them to all reach their target end level at the same time. The next thing you'll see is the next challenge our customers have is they want to be able to view all this data real time. And probably more importantly, they need to be able to record upwards of thousands of channels of strain gauges if you're talking about a large airframe. The next thing that our customers need to think about when it comes to static test is the safety of the test article. Generally speaking, full-scale static test articles are one of a kind that have taken months, if not years, and millions of dollars to assemble and instrument for the sole purpose of reaching these ultimate design levels, or these ultimate design limit loads that will open up the flight envelope. And so safety is paramount for this. And so we've helped customers with multiple layers of safety, starting with the software and the control system, but then typically graduating to either mechanical or active controlled unloads in the case of something unexpected happening. So you need to worry just as much about the unload as you worry about the loading on the way up to protect the test article in the case of an interlock or a limit trip. There's some really good videos out. I think I might post one to the chat at the end. Embraer did a really nice video on a static test showing the progression both in terms of the load level and the operators as they make their way up from 10% to 150. I find it interesting that the stress level of the airframe and the stress level of the operators seems to be pretty in sync. And then when they reach the 150 and hold it for 3 seconds, it's high fives all around. So I'll try to post that link to the chat here at the end too. Okay, I want to talk briefly about a subset, what I consider to be a subset of full-scale static testing, something that's referred to as air loads calibration. So again, I consider this to be a specialized or niche version of a full-scale static test. Customers are applying static test loads, but the big difference here is that they're applying test loads to flying aircraft. And so these are either flight test or fleet aircraft. And these are fleet aircraft that have onboard sensors, typically strain gauges, that they that are permanently installed on the flying aircraft. And the purpose of those sensors is so that they can characterize the severity of actual flights, and then they can therefore optimize their inspection intervals. So instead of just saying that we need to inspect the aircraft every 100 or 500 or 1,000 flight hours, they've realized that not every single flight hour is created equally in terms of severity and potential damage to the airframe. And so having actual onboard sensors to record exactly how severe each flight or flight hour is allows them to target this. Historically, this has been something that was primarily deployed on the military side, but we're seeing more and more customers deploy or at least evaluate the possibility of doing this on non-military and commercial platforms. A lot of value in having actual damage and damage or flight life, an objective measure of airframe life based on actual sensors and actual flights as opposed to just number of hours. So the challenges here are going to be similar to a full-scale static test. You still want synchronized uniform multi-channel loading on all your actuators, and you want all the actuators to reach their target end levels at the same time. I would say that this type of test ramps the safety requirement up even higher, because now you're not talking about a test article. Well, you're not talking about a dedicated test article. You're talking about vehicles that are planned to be flying, whether it's a flight test article or just production vehicles that are in the field. And so again, we've deployed the same types of safeties, again, starting with our controls and software, which is always the first level of defense, setting up limits, and more importantly, the actions that the system takes when those limits are breached. But in almost every one of these airloads calibration rigs, they almost always have a second, third, or fourth layer of safety in the form of some type of load abort manifold, whether that's passive mechanical, tuned orifice, or an actively controlled unload. And so MTS has multiple options in terms of sophisticated and advanced safety systems that we've helped customers with in this test space. Okay, we're going to move over to a full-scale fatigue test. This is an MTS representation of kind of what a typical fatigue test may look like in this space. Many of the eVTOL platforms are sized to allow customers to build freestanding reaction frames, which is what you see here, as opposed to integrating the actuators into the building or structure of the lab. And so you kind of see what you see here is, wiffle tree type orientation. So how we spread the load from or how our customers spread the load from a single actuator to distribute that load across the surface of the wing. And so again, with the goal here of applying uniform representative loading for what the aircraft is going to see in service. So here's one kind of representation of what the actual test spectrum looks like for a fatigue or durability test. So what are our customers trying to do with a fatigue test? They're trying to verify the structural fatigue strength of the fatigue strength of the structure. This is through repeated loading. Again, this is mostly well below the design limit load. So this is cycling the aircraft into what it sees during a typical flight, as opposed to that static test, which is 50% greater than any single load it would ever see in a flight. The fatigue test is there to enhance the safety by staying ahead of the customer's test fleet. Typically, in a test program, your fatigue test spectrum, you need to have more flights on your fatigue test article, more hours and more flights on your fatigue test article than you do on the flight test. So the fatigue test needs to stay ahead of the fleet. This also allows customers to track critical design areas, high stress or strain locations. If there are hotspots that were targeted or detected using a finite element model, customers can target their inspections and zero in on those particular strain gauges during a fatigue test. They can detect previously unknown critical areas, right? So for a typical fatigue test, there's going to be lots of inspections built in. So cycle the airframe for a number of months and then pause the fatigue test to do a very detailed inspection to look for cracks, both with lots of different technologies, both visual, but then things like X-ray and dye pen inspections to determine if there's cracks that are not visible from the outside, but are internal to the structure. A fatigue test is typically going to put multiple lifetimes of use on the airframe. And so these tests, we see customers running these tests, they can take months and even years to run the test. And so the challenges that we see with our customers in this type of test space, first is sizing of the actuators and the hydraulic system. And so for a fatigue test that's going to take months or years, you want to run as fast and accurately as possible. And so a big part of being able to run as fast as possible is sizing all the hydraulic equipment appropriately, which includes the size of the actuators, the size of the servo valves is critical. And then upstream of the actuators and servo valves is going to be the hydraulic distribution and ultimately the hydraulic power system. Tuning is critical, so customers spend lots and lots of time tuning a fatigue test article, again, to get it to run as fast as possible without sacrificing accuracy. Because you want to run as fast as possible, the other thing that's critical here is the friction level of your actuators. So the higher the friction in the actuators, the harder it is to go fast and accurate. And so MTS has spent a lot of time in the design and development of our actuators to reduce friction as much as possible. So extremely slippery actuators allow customers to run fast and accurate. Again, what you want to be able to do is synchronize the loading across all the channels. And again, you want all your actuators to reach their target end levels at the same time. The other place we've helped customers in the fatigue test space is with an integration and synchronization of a data system. So historically, you'd have a separate control system and a separate data system, and then you'd have to figure out how to synchronize both systems, operate both pieces of software, and then figure out if the clocks were the same, and if not, how to manage the clocks in terms of latency, skew, etc. What MTS has done is we've designed and developed both our own load control system and our own strain data acquisition hardware platform, and both operate under our software platform. So single software platform, and maybe more importantly, we share the clock from our controller to our data system. And so when you sample the data, you're getting all the control data and all the strain data synchronized on the same clock. Okay, the next slide here, hopefully this is visual. There's a lot going on here. Hopefully it's visible. I like to show this. It's a system functional diagram. It shows what a turnkey aerostructural test system from MTS looks like with all the signal paths and hydraulic connections. And so I'm not going to go too deep into it, but it's a useful tool. It shows you how our hardware is organized in the different layers. And so the top level here on the upper left is going to be our load control system and our strain data acquisition system. You have network communications below that. We use a server client, kind of workstation architecture, which is where the application software lives. We'll talk a little bit more about the software going forward. And then moving over to the right, what you can see is primarily hydraulics. And so hydraulic power to a service manifold where you have independent off-low high control and accumulation. From there, you distribute that single 3000 PSI source into all of your actuators, whether it's 10 or 100. You have to distribute that high pressure fluid to all your actuators. And then at the end, what interfaces with the test article is an actuator assembly. The other differentiator from MTS is when we talk about actuators, we're talking about complete actuator assemblies instead of just the cylinders, which to us means not only the cylinder, but swivel on one or both ends, integrated manifold, servo valve, dual bridge load cell, and integrated displacement transducer. So we can deliver actuators that are ready to be integrated into your test out of the box. The other thing you see here is a pressure controller. And so depending on the altitude and the mission of your typical flight, many of our customers have the need to pressurize the fuselage of the cabin during the loading of the test. So we've developed our own pressure controller that requires an air system behind it. But the benefit of the MTS air pressure control system is that our flex test load control system can command the air pressurization and synchronize it with all the loading channels. And so The pressure channel is just another channel in the same test that we can synchronize in sequence to simulate, again, ground, takeoff, cruise, and landing in terms of the pressure, and synchronize that with the various loads. Okay, kind of a summary of the entire MTS aerospace testing ecosystem. Again, the flex test control system is kind of the heart of our system. It's what's going to give you accurate and representative loading on your structure. This is scalable, it's modular and scalable, so we use standard hardware across all of our different market segments at MTS, the same closed loop control real time. But we just build the control systems based on the size and scope and characteristics that you need for your test. So that can be number of channels in terms of number of actuators you want to control, any other I/O you want for the system, so analog inputs, analog outputs, digital triggers, either in or out. And so we just assemble, and it's a modular VME-based system that we assemble and build up based on the requirements of your test using standard hardware. Again, the dedicated strain data acquisition system, we've built a platform that's really optimized for quarter bridge strain conditioning. And again, this is scalable to where a single chassis is 64 channels, but we've built systems that are in the thousands of channels. And so we just stack the chassis to get the number of strain channels that you want, hard synchronized with the controller, and all operated under one software platform. This is our software, AeroPro. We'll go into a little more detail into that going forward. It's kind of the crown jewel here. It's what your test operators, what the interface is, what you use to run the test. So this particular software platform, AeroPro, has been under continuous development for over 20 years. And so we're continuously getting feedback from our customers as to new functionality that they want to see in the platform. So it's never done. Hydromechanicals, again, we can supply everything you need in terms of hydraulic power, distribution, and actuation. Finally, service and consulting. So we have a team of systems integration engineers. These guys are experts on the hardware and software. Some of them come from a testing background. Some of them were customers before coming to work for MTS. These guys have seen just about everything, and they are the experts when it comes to installation, commissioning, training, and then future consulting if you need it. These guys are available to help you. They've seen just about everything in their decades of time working with customers, specifically in the aerospace market. These guys are dedicated just to the aerospace market, serving our customers worldwide. Okay, the software. Again, we've spent a lot of time on this software. This is dedicated to aerospace structures testing. It's designed for ease of use for large channel counts specifically. So we wanted something, again, that was scalable. We have customers that are running hundreds of channels of load control and thousands of channels of strain. And so the software is set up to be able to handle a lot of table and tab views to be able to manage and tune and collect data from all those hundreds and thousands of channels. What you see on the right is the data display. So we've spent a lot of time working on the data display. It's one of the things that customers provide feedback on the most, because everybody wants to view data a little bit differently. And so we've continuously added more and more ways to accommodate people's preference on how they want to view data: bar charts, graphs, plots, tables, pie charts, spatial representations of the aircraft. And so we're always working on the data display. We've made it so that customers, once they get their preferred workspace layout, they can save it as a template, and then they can deploy their personal data display for any test that they walk up to. The other differentiators we can talk about when it comes to AeroPro are really the ability for customers to run as fast and accurately as possible. And so specifically when we talk about fatigue testing, we have multiple different compensators that allow customers to account for stiffness of the test article and allow them to run faster. Or recently, we've been incorporating modeling, so model-based testing, model-based compensation. So where you can have a model running in Simulink in parallel to the real test. And so we can compensate and iterate using the model and the real test article to allow you to run faster. Okay, we're kind of wrapping up here. So again, just to highlight some of the advantages we've discussed, we've tried to position ourselves as the lowest risk path to success in this space. We're leveraging what we've learned in the fixed wing and helicopter market and really ground vehicle battery test market, because we see those three technologies coming together in this space. And we have the ability to help customers test today based on our history and experience with what we consider to be kind of the sources of this eVTOL market. We've talked about our control system and how it's optimized and scalable for really big tests if needed. We have features that allow you to run fast and accurate. We can integrate we can integrate data acquisition hardware platforms seamlessly with our load controls through a single software platform. And again, we offer all the hydromechanical products you need. And again, possibly the most value is the consulting engineers that we have, who again support customers around the world, who have been supporting customers for 50 years at MTS. Okay, my last slide. If you're wondering where do you start if you're trying to scope and plan a test program, the first piece of advice is to involve MTS experts early. And some of the things to consider are, what type of certification are you looking for? And so there's a lot of work up front to determine, to coordinate with the certifying agency in terms of the types of tests that you're planning to run. So that'll lead to the next one, which is planning out which types of tests and how many you need to run. You need to think about what type of data you plan to collect from the tests. And then you can start to think about lab design, test design, and planning for the actual test. From there, you need to think about structural load requirements, and then starting to size the actuators. So plan out how many actuators, how you plan to distribute the load with the number of actuators, and potentially a wiffle tree or former setup. And then last but not least, specimen safety, again, is paramount. And so these are highly complex and highly valuable test articles, and damage to a test article, again, costs money, and maybe more importantly, costs time to the test program. We've noticed in this market, it's very competitive, and customers are rushing to be able to test and certify and fly. And so specimen safety becomes even more important, because any mistake is going to cost schedule. So that's the end of my slides. As a reminder, again, please submit questions into the chat. We'll probably take a minute break here to look at some questions. Let me catch my breath. And the plan is to make the slides available to all the attendees. And we're also planning on making the video available at some point also. Thanks again for joining. Again, for follow-ups, we want you to initially contact your local MTS representative, who will typically contact Jonas or I, or both of us, depending on the geography and location of the customer. But we're really interested in helping you guys move forward in this space. Thank you.